Hello students, welcome to my YouTube channel RD Academy. So in this video we will be discussing about section 1.8. The topic name is electric field. Okay, so whatever we have learned till now, it forms the basics for studying of this particular section. So first let us try to define what is an electric field. Okay, so now assume we have a positive charge Q1. Okay, now if I bring another small positive charge, okay, let us assume this is also positive charge plus Q. There is no subscript for that like Q1 and Q2, it is just Q. What will happen? By our knowledge of Coulomb's law, we already know that like charges will always repel. So this plus charge and this plus charge will repel. This will start to move in this direction, this will start to move in this direction. Okay, now assume this charge is not there. Now what happens? You have only charge Q1. Now can you say that there is nothing in the surrounding medium of this charge? Can you really say that? Because if there is nothing when there are no other charges present in its vicinity, the moment you bring another positive charge plus Q, what happens? It starts to move. And you, from your knowledge of Newton's law, you already know that whenever something is moving, there should be some external force acting on it. Okay, so now that is where this particular concept of electric field comes into picture. Okay, so in the absence of any external charge, if you have two charges plus Q and minus Q, what happens? In the surrounding medium there will be some electric field due to the charge itself. Okay, it is not necessary that you need to bring an external charge. Due to the existence of charge itself, there will be some electric field due to that particular charge. And the moment you bring this external charge to this particular point, what happens? This electric field exerts a force on that particular charge and it starts to move. Okay, so electric field is nothing but a way in which we can explain why two like charges move away from each other or two unlike charges attract towards each other. Okay, now there is one standard convention associated with the electric field. Firstly, for a positive charge, always the electric field lines diverge radially outwards. That is, they start from the charge and move outwards in outward direction. This is also known as the diverging radially outward. Similarly, for a negative charge, the electric field lines converge radially inward. Okay, these two words are important. For a positive charge, the electric field lines diverge radially outward, whereas for a negative charge they converge radially inward. Okay, so this is the 2 points you need to remember. Now we will try to define. Now you have understood qualitatively what is an electric field. It's just nothing but the field that exists around the charges. The moment you bring another charge, what happens? This electric field exerts a force on this particular charge and it starts to move. Okay, so now if I try to define it mathematically, how can I do that? See, even in the absence of this charge, electric field exists due to this big charge, right? So let us call this charge as capital Q. Okay, now can you tell me on what all factors this electric field is depending? Firstly, it is depending on the magnitude of the charge, not the charge you are bringing, but to the magnitude of the charge itself. Second one is the distance from where you are measuring. Obviously, this strength of the electric field line keeps on decreasing as you move away from the charge. So the second quantity depends is on the distance r from the charge itself. So the magnitude of electric field is given by 1 by 4 pi epsilon naught capital Q divided by r square into r cap. Okay, let us try to read this. This is electric field, and again electric field is also a vector quantity. You need to remember that it is directly proportional to this proportionality constant 1 by 4 pi epsilon naught This Q is the magnitude of the charge that is producing the electric field. Okay, not the small charge that I am bringing. There are two separate names for that. I will discuss that within a short while. Then this R is the distance from this point charge. For example, if I have a positive charge here and I am finding out the electric field at this distance, R indicates the distance from the charge producing electric field to the point of interest where you are finding the electric field. Okay, now what is this R cap? As you know previously, this electric field is a vector. This whole thing here is a number, magnitude. Now I need to indicate one direction, right? So this R cap indicates the direction. If it is a positive charge, this is the direction of R cap. If it is a negative charge, this will be the direction of R cap. Okay, now assume this charge Q is producing some electric field E around it. Now I am bringing another charge, small q. Okay, this is capital Q, the source of the electric field. This is the small q. Now what is the force between these two charges? F is equal to, from Coulomb's law, F vector is equal to 1 by 4 pi epsilon naught. First charge is capital Q, the second charge is small q. Q into Q divided by, again, R square into R cap. Now this R square is the line joining these two charge systems. Okay, now can you see one relation between these two quantities, that is electric field and electrostatic force of attraction or repulsion? See, you have 1 by 4 pi epsilon naught. Here also you have 1 by 4 pi epsilon naught. Here also you have Q by R square R cap. Here also you have Q by R square R cap. The only missing term is this small q. So I can write the electrostatic force of attraction or repulsion. This entire thing apart from this small q is nothing but your E. Your E vector multiplied by Q, or your electric field is nothing but ratio of electrostatic force to the charge. Now can you tell me what is the SI unit of electric field? SI unit of force is Newton, SI unit of charge is Coulomb. So the SI unit of electric field is Newton per Coulomb. Now one homework for you, try to write the dimensional formula of the electric field. Okay, just substitute dimensions of force and dimension of charge, you will get the dimension of electric field. So try to solve that. So I hope it's clear. Electric field is nothing but the field around the charge, okay, wherein if you bring another charge, it will experience electrostatic force of attraction or repulsion. Fine. Now there, as I've said previously, there is one special name for those two charges. Okay, always remember, while solving numericals, they will ask you to find the electric field due to some charge capital Q at a distance P, which is at a distance R from it. Okay, now this charge, which is the source of the electric field, is called as source charge. Okay, the another field, now I am here, there is no other charge. The other charge that you bring to experience the force, what happens if I bring small q here? Then this electric field here, which is in this direction for a positive charge, will exert an electrostatic force on this small charge and it will move in this particular direction. Okay, now source charge is that particular charge which produces the electric field. Okay, test charge is that particular charge which experiences the electric field. Okay, I hope there is no doubt between source charge and test charge now. Fine. As we have seen previously, electric field is nothing but ratio of electrostatic force experienced per unit charge. It implies that if you have no charge here, initially you had no charge at this point, right? So if the moment you bring another charge q, how much force it will experience, that quantity, that particular ratio is known as the electric field. Fine. I hope I have been clear about both qualitative and quantitative definition of electric field. What is the other formula here? electric field, you can also write it as 1 by 4 pi epsilon naught. If you are writing charge wise, then you just need to write the magnitude of source charge, the charge that is producing the electric field, divided by, now you are finding the electric field at this point P, right, which is at a distance r from the source charge. So in the denominator you will get r square. The direction is given by r cap. So for a positive charge, this is the r cap. For a negative charge, it will be in the opposite direction. Okay, so I hope this is very clear to you. And there is one special property for this electric charge. Okay, now it depends only on magnitude. First quantity, it depends, this 1 by 4 pi epsilon naught is constant, right? That is constant. Okay, the first quantity it depends on is magnitude of source charge, or the charge that is producing the field. Second distance, r, that is the distance from source charge to the point where you are finding the electric field. These are the only two factors on which the magnitude of electric field depends. Now can you tell me, suppose for this example, okay, that magnitude of charge Q, it doesn't change, it remains the same. So this quantity, first quantity, remains the same. What happens if I keep this also same, the distance from where you are measuring the electric field? Then the magnitude of electric field also should be same, right? So in other words, if you move same distance r in another direction, and if you consider this is point P, both magnitude of electric field here and at here, both should be same. Why? Because the magnitude of charge is same and magnitude of distance between them is also same. Okay, so this special property is known as spherically symmetric. Okay, you should say that electric field is spherically symmetric in nature. Why? Now if I consider different points like this, all these points which is at same distance r from the test charge, what happens if you join in a two-dimensional plane? That is, on this paper it is a circle. What happens in three-dimensional plane? The extension of circle in three-dimensional plane is nothing but the sphere. Okay, so in a sphere, if you keep the radius of the sphere same, then the magnitude of the electric field at all points remain the same. Okay, this property is known as spherically symmetric property of the electric field. Fine. Now another one important topic in this electric field is electric field due to multiple charges. Okay, now we have already seen what a principle of superposition is. What is principle of superposition? When you have more than one charge system, the net force acting on any charge is nothing but the vector sum of all the forces acting on that particular charge. Now also, here also consider three charge system. You have charge Q1, you have charge Q2, you have charge Q3. Okay, but since we are discussing with the electric field, these are the only three charges that I need. Okay, these are the source charges, the charges that is producing the electric field. Now consider point P in a three-dimensional plane. Let this distance from charge Q1 to point P be R1P. Let this distance be R2P. Let this distance be R3P. Okay, now what this electric field due to multiple charges tells you is that it also obeys principle of superposition. Okay, electric field also obeys principle of superposition. So previously what you have learned for charges, for force, just extend that here. Here it says that if you have more than two charge system or more than a single charge, the net electric field at any point P in a three-dimensional plane is nothing but sum of the individual electric fields at that point due to all other charges. Okay, now consider this system, consider this point. Now ignore Q2 and Q3, consider only charge Q1. Okay, now what is the electric field at point P due to charge Q1? That I will represent it as E1P, and you will read it as electric field due to charge Q1 at point P. Similarly, second one, while dealing with charge q2, ignore charge q1 and q3. Now you can write, for charge q2 you can write it as electric field due to charge q2 at point P. Similarly, for this one, ignore these two, you will get electric field at due to charge q3 at point P. Now this is for 3 charge system. What happens if you extend it to n charge system? Here also you will get n charge electric field due to charge qn at point P. Fine. Now let us simplify it mathematically. What can I write? This electric field, I can write it as, here I have already written the expression. Electric field I can substitute it as 1 by 4 pi epsilon naught magnitude of the charge divided by the distance square multiplied by the unit vector. Okay, now apply the same formula. What I can write, E1p as this 1 by 4 pi epsilon naught is a constant. Now the charge, when you are discussing with the electric field, you should only consider the source charge. Now which charge is responsible for this particular electric field? This charge q1. So here you will get q1, that's it, there won't be any other charge. Remember, while you are dealing with electrostatic force, you will get 2 charges. When you are dealing with electric field, you will get only 1 charge. So q1 divided by, now what is the distance between q1 charge and point P? r1p square. Now this is just the magnitude, but here I have a vector symbol, so I should also include one vector sign, right? So that will be r1p cap. For a positive charge, it will be in this particular direction, radially outward. Okay, now similarly, can you write it for E2p, that is electric field due to charge q2 at point P? Now I can write it as 1 by 4 pi epsilon naught, which charge is responsible for field to q2 divided by distance between charge q2 and point P is r2p square into r2p cap. Okay, similarly for E3p will be, this constant term will remain same, but here it will be q3 r3p cap. Now I will directly write it for nth charge. Okay, for nth charge it will be 1 by 4 pi epsilon naught q3 divided by r3p into r3p, sorry, rnp into rnp cap. Fine. Now simplify it. Now which are all the terms that is common here? 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught. Take it outside. 1 by 4 pi epsilon naught, in bracket you have q1 by r1p square into r1p cap plus q2 by r2p square r2p cap up to qn nth charge rnp into rnp cap is equal to 1 by 4 pi epsilon naught. This whole term I can simplify using summation symbol. Give one alphabet I. From where it starts? I starts from 1 and it goes on till n. Okay, I starting from 1 to n. qi divided by ri, this p is constant in all the terms, rip square into rip cap. Okay, the summation sign just indicates the plus sign. First term will be I equal to 1, q1 r1p square r1p cap here. Next will be plus I starts from 1 and it goes on till n. So then you will substitute in place of I to write the second term, go on till the nth term. Okay, so this is the net electric field at point P. Fine. I hope clear. I hope I'm clear in this explaining this topic. Okay. Next, there is small section in your NCERT book called as physical significance of electric field. Now, before learning anything, always ask yourself, is it really necessary? For example, here when you are dealing with 2 charge system or 3 or n charge system, we have already seen what is the force between them, right? And we, through principle of superposition, we calculate the net force. Then what is the need for separately studying this electric field? See, for in your first chapter, as I've said in the introduction video, you are dealing only with the electric statics, that is charges are at rest. This particular concept of electric field is highly important and most useful when this charge starts to move with the velocity v. Okay, then to experience the force between multiple charges or things like that, higher order physics concepts, this electric field is necessary. Okay, so in one statement I want to say, I can say that electric field is convenient. Okay, it is useful but not really necessary for the study of electrostatics. Okay, it is only an elegant way of characterizing this electrostatic environment of the system of charges. Like if you have a charge, what is its environment, like nearby surroundings, what is happening, what is there. To explain those concepts you need electric field. Okay, and electric field is a characteristics of the system of charges. Always remember, it depends only on the source charge. It does not depend on the magnitude of test charge. It only depends on source charge. It does not depend on test charge. Fine. And this concept of electric field was first invented by a scientist named Faraday, and at present it is one of the most highly used concept in physics. Okay, so while coming to these topics, this principle of superposition is important. There will be one numerical for 5 marks in your board exam, or this diagram, sometimes they will ask this for 2 marks. Draw the electric field representation for a positive and negative charge. Fine, I hope I am clear in this topic. If you have any doubt, please ask in the comment section. Thank you.